properties of the natural log function. So again, the natural log is the ln of x, domain is positive, range is all reals, it's continuous over its domain, has the asymptote as the y-axis, which we went over when we looked at the graph. All right, the rules or properties of logarithms. So if n and p are positive, right, I can only put positive numbers in, or expressions. An expression would mean it'd be something like x plus 2, an algebraic expression. All right, so remember, and hopefully you've again seen these somewhere before, if I've got p times n, I can split that into np plus the natural log of p plus the natural log of n. So if I've got something like this, the natural log of 2x times x plus 1. Well, I can rewrite that as the natural log of 2x plus the natural log of x plus 1, which actually, the derivative is a lot easier in the second expression than the first expression. If I've got division, and again, remember, inside the function, so I've got p divided by n, I can rewrite that as the natural log of p minus the natural log, and it should be n, not n, that was a typo. N. So if I've got something like 2x divided by, let's do x plus 1 divided by 2x. Right, I can rewrite that. Now when you rewrite it, you have to be more careful with the division. It's always the numerator first, natural log of x plus 1, minus the denominator inside the log. And so you'll notice, when I go from the division inside, I get 2 logs that are subtracting outside. When I go from multiplication inside, I get the addition of 2 logs on the outside. And equal means I can actually go both directions if I wanted to. If I wanted to go from 2 logs to 1, I could use this property. If I wanted to, again, go from subtracting 2 logs to just having 1 log, I could use this property. All right. This one is the one we're probably going to use the most in this class, to simplify to find derivatives. All right, so if I've got p raised to n, what I can do is I can pull that power n out front, and I get n times the natural log of p. And so where we'll use this, suppose I have the natural log of the square root of x plus 1. Well, remember, the square root is the 1/2 power, and so 1/2 is the n part, that's the power, and I can pull that 1/2 out front. And so I can change this to 1/2 times the natural log of x plus 1. And so I no longer have a root. And it's a lot easier to find a derivative without a root. And I can do that with any power. Had it been to the cube, I could have pulled the cube out. So if had it been something as simple as natural log of x cubed, well, I could do the same thing. 3 times the natural log of x. This first expression would require the chain rule. The second expression does not in this case. And so it's a lot easier if I could avoid using the chain rule. So that's why this third one is going to be very helpful when we get to derivatives. The last 2 are general cases, which again, you can plug these into your calculator and check that they're true. Natural log of 1 is 0. Type it in, it's true. The natural log of e, well, remember, the natural log is the inverse of the exponential base e function, and so it should make sense to cancel each other out and leave me with 1. Again, you can type it in your calculator and see. These 2 expressions allow me to solve equations, which we'll be using. If I get e raised to the natural log of x, well, the e and the natural log undo one another, leave me with x. And the same thing's true if I write it in the other order. Natural log of e to the x, again, natural log and e are inverses. They undo each other and will leave me with the x value. All right. The uniqueness property. All right, I can take the natural log or the exponential of both sides. So if I've got some expression, so suppose I've got something like this. E to the 2x equals 10. Well, I want to solve for the 2x. So I could take the natural log of e to the 2x and the natural log of 10, and then that allows me to solve it a little easier. Or if I've got the natural log of 2x equals 5, I can take it raised to the e. E raised to the natural log of 2x equals e raised to the 5. And then I can use that inverse property and solve. And so these are the uniqueness property allows me to solve it. We'll get to solving in the next video, but that's what this allows me to do. And then the part 2 is just the reverse of that. If I've got the natural log of x equals the natural log of 2, well, x has to equal 2, right? If I've got e to the x equals e to the second, well, again, x has to equal 2. And that should just make sense that that's the case. If I've got the same base, my exponents have to be equal, and if I have the same natural log on both sides, what's inside the natural log has to be equal. All right, and so those last two properties, this uniqueness property and these two, allow us to solve equations with exponentials and logarithms. And so that's what we're going to get into. In the next video, I'm going to solve equations of exponentials and logarithms, and then we'll get to applications of exponentials and logarithms. All right, so those are properties. We'll stop there.